The ocean, our planet's vast and mysterious heart, pulses with a rhythm that is felt rather than heard. It is a slow beat, it is a deep beat, it is an unending beat. On the surface, under the steady gaze of the equatorial sun, the water shimmers, absorbing heat and growing warm. 1,000 meters below, in the crushing darkness of the abyss, a different world exists. Cold water flows, carrying the chill of ancient ice. Between two realms, the sun-kissed surface and the deep, cold dark, lies a simple, profound difference in temperature. A gradient that never sleeps, a quiet power source waiting to be tapped. This subtle temperature difference, often no more than 20 degrees Celsius, is the secret engine of our planet's climate. It drives currents, it fuels weather systems, it nurtures ecosystems of incredible complexity. For over a century, engineers and visionaries have seen in this thermal divide a source of clean, inexhaustible power. This is ocean thermal energy conversion, OTEC. The ocean is a colossal thermal battery continuously charged by the sun. OTEC seeks to harness that stored energy, turning the thermal heartbeat of the sea into electricity for our modern world. Not the roar of wind, nor the blaze of solar, this energy is gentle and diffuse. It does not roar or blaze, it simply exists across the tropical seas. The challenge is capturing it efficiently. We must work with nature, sipping energy from a vast reservoir rather than burning it in a burst. OTEC's story is one of ingenuity building machines that operate on subtle differences, turning a whisper of heat into steady work. It's a tale of persistence, of trial and error, of growing understanding of the ocean's systems. This journey is not just technology, it's a vision for a different future. Imagine coastal cities. Imagine island nations often dependent on expensive, polluting imported fuels, drawing power directly from the surrounding waters. Imagine a power that runs 24 hours a day, 7 days a week without the smoke of fossil fuels and without the intermittent nature of other renewables. This is OTEC's promise, a clean, reliable, predictable source of baseload power, not from a roaring furnace, but from the steady, silent pulse of the sea. A story of living in greater harmony with our planet, using its quietest forces to build a more sustainable world. If you live within the tropical belt, the ocean stretching out from your coastline is far more than just a beautiful vista. It is a vast thermal engine, spread across thousands of square kilometers working tirelessly day and night. The physics at play are remarkably straightforward. Sunlight warms the surface layers of the ocean to a pleasant temperature, typically around 25 degrees Celsius, around 30 degrees Celsius. This warm water forms a massive, stable layer that can extend down for 100 meters or more. Far below, in the perpetual twilight of the deep ocean, the water remains profoundly cold, near 4 degrees Celsius, near 5 degrees Celsius. This permanent stratification creates a vertical temperature gradient, a thermal cliff that holds an immense amount of potential energy. OTEC is the technology designed to capture this potential and convert it into usable electrical energy. At its core, the concept sounds deceptively simple. You move heat from the warm surface water to the cold deep water, and in the process, you use that transfer of energy to spin a turbine and generate electricity. It is the same fundamental principle that drives every heat engine, a steam locomotive, a nuclear power plant. However, the great challenge of OTEC lies in the gentleness of the gradient. A conventional power plant might operate with temperature differences of hundreds of degrees, creating high pressures and powerful flows. OTEC must work with a mere 20-degree difference, a delicate thermal slope that demands extraordinary care in its design. This gentle gradient means that every component in an OTEC system must be optimized for maximum efficiency. Every valve must seal perfectly, every pump must move water with minimal effort, every pipe must be insulated to prevent precious degrees of temperature from being lost to the environment. The heat exchangers, which are the heart of the system, must be designed to transfer thermal energy with incredibly low losses. The entire plant is a testament to the art of low-loss engineering, a closed loop of energy stewardship where every joule is respected and conserved. The guiding philosophy is to move the absolute minimum amount of water necessary exchange heat with surgical precision and convert that heat into work with relentless efficiency. When this is done right, however, OTEC offers something truly rare and valuable in the world of renewable energy baseload power. Unlike solar panels that go dormant at night or wind turbines that stand still on a calm day, an OTEC plant can run continuously, around the clock, for weeks and months on end. The ocean's thermal gradient is remarkably stable, changing only by a few degrees with the seasons. This makes OTEC a predictable and steady source of electricity, capable of anchoring a power grid and providing the constant energy supply that modern societies require. It is a quiet, unassuming workhorse, a perfect complement to the more variable renewable sources that are becoming increasingly common. The power of ocean thermal energy conversion extends far beyond simple electricity. While providing clean, stable electricity is its primary function, a well-designed OTEC plant can become the cornerstone of a sustainable blue economy. The process creates valuable co-products that can transform coastal economies, especially remote islands. The same process that generates power also yields desalinated water. That water is scarce and costly where OTEC works best. This fresh water can support local agriculture. It can provide clean drinking water. It can reduce dependence on imports and energy-intensive reverse osmosis. The benefits don't stop with water. Cold, deep seawater pumped to the surface is a resource too. It's cold and remarkably pure. It's also rich in nutrients settled over centuries. After passing through the OTEC condenser, this slightly warmed but still cold water can be repurposed. It can be piped into buildings for efficient air conditioning. This is seawater air conditioning SWAC. SWAC can slash electricity use in hotels, in hospitals, and in data centers. The nutrient-rich deep water is ideal for aquaculture. In sunlit surface waters, those nutrients are quickly consumed by phytoplankton. Bringing deep water into controlled ponds or tanks creates ideal growing conditions for high-value algae, for shellfish, for cold water fish like salmon and sea bass. That opens opportunities for food production and exports. It diversifies local economies. And it creates skilled jobs. An OTEC facility can become an integrated hub of productivity, linking energy systems, water systems, and food systems in a virtuous cycle. Each supports and enhances the others. This integrated vision is the true promise of OTEC. It is not just a power plant, it's a catalyst for resilient, self-sufficient coastal communities. Imagine an island insulated from volatile fuel prices with abundant fresh water and new industries in cooling and aquaculture, creating prosperity. This is the potential of the ocean's thermal gradient. By working with this gentle, persistent energy source, we can do more than power homes. We can build a new relationship with the ocean, stewardship, innovation, and a shared sustainable future powered by the steady rhythm of the sea. At the very heart of ocean thermal energy conversion lies a fundamental principle of physics, one that governs everything from the steam engine that powered the Industrial Revolution to the internal combustion engine inside a modern car. This is the science of thermodynamics, the study of how heat moves and how it can be converted into useful work. All heat engines, without exception, operate on a simple and elegant logic. They take in heat from a hot source, convert a portion of that heat into mechanical work, and then reject the remaining waste heat to a cold sink. Think of a steam train. Burning coal creates a hot source, which boils water into high-pressure steam. This steam pushes a piston doing work, and the cooled lower-pressure steam is then released into the colder surrounding air. The key to making any heat engine work is the temperature difference, or delta T, between the hot source and the cold sink. The greater this difference, the more efficiently the engine can convert heat into work. A power station burning natural gas might operate with temperatures soaring to hundreds of degrees Celsius, creating a massive thermal gradient that allows for high efficiency. OTEC, however, operates in a completely different realm. Its heat source is the warm surface water of the tropical ocean, at a gentle 25 degrees Celsius, 30 degrees Celsius. Its cold sink is the frigid deep ocean water, at around 4 degrees Celsius. 5 degrees Celsius. The temperature difference is small, only about 20 degrees. This is the central scientific challenge of OTEC. Because the thermal gradient is so gentle, the theoretical maximum efficiency of an OTEC plant is low, typically only a few percent. This is not a flaw in the technology, but a simple reality dictated by the laws of physics, specifically the Carnot cycle, which sets the upper limit for efficiency. This means that for every unit of thermal energy that flows through the system, only a tiny fraction can ever be turned into electricity. The vast majority must be rejected as waste heat. Therefore, an OTEC plant must be a master of volume. It has to process enormous quantities of water to extract a meaningful amount of energy. This low efficiency dictates every aspect of OTEC's design. It forces engineers to think not in terms of high pressures and temperatures, but in terms of minimizing every possible loss. Frictional losses from water flowing through pipes, heat losses through inadequate insulation, and mechanical losses in the turbine and pumps all become critical factors. A loss that would be negligible in a conventional power plant could be enough to render an OTEC plant useless, consuming more power than it generates. The science of OTEC is therefore a science of subtlety. It is about designing a system so exquisitely tuned that it can coax useful work from one of nature's most gentle yet most persistent energy gradients. To understand how OTEC turns a slight temperature difference into electricity, we must look at how fluids behave. The key is a process called phase change, the transition of a substance from a liquid to a gas or vapor. When a liquid boils and turns into vapor, it expands dramatically. It is this expansion that can be used to spin the blades of a turbine. We are all familiar with water boiling at 100 degrees Celsius at sea level. However, the boiling point of a liquid is not fixed. It depends entirely on pressure. If you lower the pressure, you can make a liquid boil at a much lower temperature. Lower pressure equals lower boiling point. This is the secret that unlocks the potential of OTEC. It allows us to create vapor and drive a turbine using only the modest warmth of surface seawater. In an OTEC system, the warm surface water provides the energy needed to boil a working fluid. The cold deep water then provides the means to condense that vapor back into a liquid, completing the cycle. The entire process is a carefully choreographed dance between temperature and pressure. The warm water flows into a device called an evaporator, where it transfers its heat to the working fluid. The resulting vapor, now under pressure, is channeled to a turbine. As the vapor expands and cools through the turbine, it spins a generator, producing electricity. Finally, the low-pressure vapor enters another device, the condenser, where the cold, deep seawater absorbs its heat, causing it to change phase back into a liquid, ready to be pumped back to the evaporator to start the cycle anew. The challenge is that with only a 20 degrees Celsius difference to work with, the pressures and flows generated are very delicate. The vapor produced is not the high-pressure, superheated steam of a traditional power plant. It is a low-pressure, low-density vapor. This means the turbine must be exceptionally large and exquisitely engineered to capture energy from this gentle flow. It must spin with minimal friction, its blades shaped to interact perfectly with the moist, low-velocity vapor. Every component in the cycle must be designed to work with these small differences, from the massive heat exchangers that transfer heat with minimal loss to the powerful pumps that must move vast volumes of water efficiently. This delicate balance explains why OTEC has been such a long-standing engineering puzzle. It is not a matter of raw power, but of immense finesse. The system must be perfectly sealed to maintain the precise pressures needed. The pipes and heat exchangers must resist corrosion and resist fouling from the constant flow of seawater, which would otherwise degrade performance. The entire plant is a testament to precision engineering, where success is measured in fractions of a degree and tiny gains in efficiency. It is the science of working with a whisper of energy, not a roar, and turning that quiet, constant thermal whisper into a steady, reliable hum of electric power. As engineers have grappled with the unique challenges of OTEC, they have developed three main approaches to designing the power cycle. Each pathway has its own distinct advantages and complexities. Closed, open, hybrid. The closed cycle system uses a sealed loop with a low-boiling working fluid like ammonia. That working fluid is boiled and condensed to drive the turbine, while ocean water only heats and cools the outside of the heat exchangers. Because ammonia boils at a very low temperature, it can create high vapor pressure from modest surface heat, yielding a smaller, more powerful turbine. The system is self-contained, which keeps core machinery away from corrosive seawater. The main challenges are building extremely large, highly efficient heat exchangers, and ensuring the loop stays perfectly sealed to prevent any ammonia leakage into the ocean. The open cycle system uses the warm seawater itself as the working fluid. Surface water is drawn into a Nero vacuum chamber. At low pressure, a fraction of the water flash evaporates into low-pressure steam. That steam then drives a turbine. When the steam is condensed with cold deep seawater, it becomes desalinated fresh water. So open and cycle OTEC co-generates electricity and produces highly valuable desalinated water, a huge benefit for arid coastal regions and island nations. Hybrid systems combine the best of both approaches. A typical hybrid uses an open-cycle front end to flash evaporate warm seawater, producing steam and fresh water. That steam is then used to boil a working fluid like ammonia in a secondary closed loop. This configuration can optimize energy extraction while still producing desalinated water. Hybrids are more complex, but they offer flexibility. Plants can be tailored to maximize power output, or to maximize freshwater production, or to find a balanced combination of both, depending on local needs. The journey of turning the ocean's gentle heat into electricity begins with a deceptively simple first step, bringing the warm surface water into the power plant. This is the warm water intake, the mouth of the OTEC system. Large diameter intake pipes sit just below the ocean surface, drawing sun-warmed seawater. Commercial-scale plants move millions of liters every minute. The aim: capture the warmest water using as little energy as possible. Pumps that drive this flow are a major internal energy cost. Parasitic loads. Engineering the intake is a balancing act. Hydraulics ecology. Intake openings are covered with large screens to protect wildlife, fish, turtles, other marine life. Intake velocity is kept below the swimming speed of most small fish, so they can swim away unharmed. These structures, called velocity caps, create a gentle, non-threatening flow. OTEC aims to work in harmony with marine ecosystems and local communities. Material choice for pipes matters. Steel corrodes fast in warm, oxygen-rich surface water. Modern designs favor glass fiber reinforced plastic high-density polyethylene. These materials resist corrosion and are lighter, easing installation on floating platforms. Pipe routes are planned short and direct to minimize friction. Less friction means less pumping energy. Warm seawater then travels into the plant. It passes through filters, debris screens to remove smaller particles. That protects downstream equipment, especially the heat exchanger. Every element of this stage is tuned for efficiency and sustainability. From slow intake velocities to low-friction pipe materials, the system delivers maximum thermal energy with minimal environmental impact and low internal energy cost. After being drawn into the plant, warm surface seawater being pulled through intake pipes arrives at the first of two critical heat exchangers, the evaporator. This component is truly the heart of the closed-cycle OTEC system. It is here that the ocean's thermal energy is transferred to the working fluid, causing it to change from a liquid to a vapor. The working fluid of choice is typically anhydrous ammonia. Ammonia is selected because it has a very low boiling point around -33 degrees Celsius at normal atmospheric pressure. At the slightly elevated pressures inside the OTEC system, it will readily boil when exposed to seawater that is a mere 25 degrees Celsius, 28 degrees Celsius. This property allows the system to generate vapor without needing a high-temperature heat source. The evaporator itself is, honestly, an engineering marvel of surface area and efficiency. It usually consists of thousands of thin plates, small diameter tubes typically made of titanium. Titanium is the preferred material because of its exceptional resistance to corrosion from seawater and its ability to conduct heat effectively. These plates or tubes are stacked bundled together, creating a labyrinth of channels. The warm seawater flows on one side of these thin metal walls, while the liquid ammonia flows on the other. The key is to maximize the surface area for heat exchange, allowing the thermal energy to transfer from the water to the ammonia as quickly and completely as possible. The design must achieve this high heat transfer rate while keeping the pressure dropped to an absolute minimum. As the seawater flows through the evaporator, and ammonia flows through the evaporator, they encounter friction, which causes a loss of pressure. This pressure drop requires the pumps to work harder, consuming more of the very electricity the plant is trying to generate. Therefore, engineers meticulously design the internal geometry of the evaporator to ensure smooth, low-turbulence flow paths. They are constantly chasing a delicate balance, creating enough mixing to ensure good heat transfer, but not so much that it creates excessive friction. Every fraction of a degree of temperature transferred, and every fraction of a bar of pressure saved, contributes directly to the plant's net power output. As the liquid ammonia absorbs heat from the seawater, it begins to boil vigorously, transforming into a high-pressure vapor. This phase change is the engine of the entire cycle. The once liquid ammonia expands dramatically, its volume increasing many times over. This expansion creates the pressure that will soon be used to do work. The slightly cooled seawater, having given up a few degrees of its thermal energy, is then channeled away to be returned to the ocean. Meanwhile, the pressurized ammonia vapor is now ready for the next step, its journey to the turbine, where its stored energy will finally be converted into motion. The high-pressure ammonia vapor, now carrying the thermal energy harvested from the warm surface water, is directed through heavily insulated pipes towards the turbine. This is the moment of conversion. Thermal potential becomes mechanical energy. Cutaway CGI. Watch the vapor flow, strike the blades and transfer energy. The OTEC turbine is specialized, different from conventional steam turbines. OTEC works with a very small temperature difference, so the pressure ratio across the turbine is quite low. The vapor doesn't expand with the explosive force of high-temperature steam. To compensate, OTEC turbines handle a very large volume of low-density vapor. They have very large blades. They feature a wide diameter. Design focuses on aerodynamic efficiency above all else. Every curve of the blades is sculpted to keep vapor flowing smoothly and minimize turbulence. The bearings must be extremely low friction to avoid wasting precious mechanical energy. Every detail is optimized for this low-pressure, high-volume environment. As ammonia vapor expands and pushes the blades, the central shaft rotates at high speed. That rotation is the mechanical work the engine produces. The expanding vapor loses pressure and temperature as it transfers energy to the spinning turbine. It enters as warm, high-pressure vapor. It exits as cooler, low-pressure vapor. This expansion and rotation continuously drives the power generation system. The turbine's shaft is directly connected to a generator. Inside the generator, spinning motion becomes electrical energy by electromagnetic induction. Powerful magnets move past coils of wire, inducing an electrical current. This electricity is then conditioned by power electronics. Voltage and frequency are synchronized for the local power grid, or routed through an undersea cable to shore. The sunlight-warmed surface water's small temperature difference has now become clean, stable electricity ready to power homes and industries. After the ammonia vapor has done its work in the turbine, it must be turned back into a liquid so it can be pumped back to the evaporator to repeat the cycle. This is the crucial role of the condenser, the second major heat exchanger in the system. To condense the low-pressure ammonia vapor, a powerful cold source is needed. This is where the other half of the ocean's thermal gradient comes into play, the deep, cold seawater. This water is drawn from depths of 700 to 1,000 meters, where the temperature is a stable 4 degrees Celsius, 5 degrees Celsius. Getting this water to the plant is one of OTEC's most significant and iconic engineering feats. The cold water pipe is the lifeline of the OTEC plant. It is a massive structure, often several meters in diameter and a kilometer long, reaching from the plant on the surface down into the ocean's twilight zone. This pipe must be incredibly strong to withstand the immense pressures of the deep ocean, as well as the dynamic forces of waves and currents at the surface. It is typically constructed from advanced materials like fiber-reinforced composites or steel with specialized coatings. Furthermore, the pipe must be well insulated to prevent the cold water from warming up, as it is pumped through hundreds of meters of warmer surface water. Inside the condenser, the cold, deep seawater flows through a network of titanium plates or tubes. The low-pressure ammonia vapor from the turbine flows over the other side of these chilled surfaces. As the vapor comes into contact with the cold metal, it rapidly loses its remaining heat to the seawater. This loss of thermal energy causes the ammonia to change phase, condensing from a gas back into a liquid. This phase change happens at a very low pressure, which is essential for maintaining the pressure difference across the turbine that keeps it spinning. The efficiency of the condenser is just as critical as the evaporators. Once condensed, the liquid ammonia is collected in a reservoir. It has now completed its journey through the power-generating part of the cycle. From the reservoir, a high-pressure pump, the only major energy consumer in the working fluid loop, sends the liquid ammonia back to the evaporator to be heated and vaporized once again. This completes the closed cycle. The ammonia working fluid circulates continuously within its sealed loop, used over and over again. The seawater, having absorbed the waste heat, is now slightly warmer and is discharged back into the ocean at a carefully selected depth to minimize environmental impact, closing the thermal loop and sustaining the plant's continuous operation. Open-cycle OTEC uses warm surface seawater itself as the working fluid, eliminating the need for a separate substance like ammonia. Instead of recirculating in a closed loop, seawater is drawn in, flashed into steam under low pressure, drives a turbine, and is discharged. By lowering the pressure in a vacuum chamber, seawater boils at much lower temperatures, around 25–28 degrees Celsius, making direct energy extraction possible. This design removes the need for a massive heat exchanger, reducing costs and biofouling risks, but demands a large, robust vacuum chamber and constant removal of non-condensable gases. The engineering focus shifts from managing high-pressure fluids to maintaining a stable vacuum and handling vast volumes of low-pressure steam. Open-cycle OTEC turns seawater into both the fuel and the product, offering a direct, integrated approach to ocean thermal energy. The flash evaporator is the heart of open-cycle OTEC, where warm seawater enters a vacuum chamber and instantly flashes into low-pressure steam. Only a tiny fraction of the water vaporizes, cooling the rest. The resulting steam is cool, low density, and requires a massive, specialized turbine to extract energy. Saltwater droplets in the steam can corrode turbine blades, so advanced mist eliminators are essential for protection. Vacuum pumps must constantly remove released gases to maintain low pressure. Their efficiency is crucial for net power output. The process is a delicate balance, maintaining the vacuum while generating power from the ocean's gentle temperature difference. Every component must work in harmony to make open-cycle OTEC viable. After powering the turbine, the low-pressure steam is condensed, ideally using a surface condenser cooled by deep seawater to produce exceptionally pure, desalinated fresh water. This process is essentially single-stage distillation, yielding water often purer than municipal supplies. For many tropical islands and arid coasts, this fresh water is as valuable as the electricity generated. OTEC's dual-output power and water can transform local agriculture, health, and economic resilience. The ability to co-generate both resources strengthens the business case for OTEC, making it a sustainable infrastructure solution. Open-cycle OTEC is more than energy, it's a platform for sustainable development. Hybrid OTEC systems combine open-cycle processes and closed-cycle processes. Open-cycle flash evaporation produces fresh water. It also produces steam. That steam vaporizes ammonia in a closed-loop heat exchanger. The ammonia vapor then drives turbines to generate electricity. This approach delivers desalinated water and efficient electricity. It protects turbines from corrosive seawater steam. The system separates water production and power generation, making each easier to optimize and maintain. Hybrid OTEC can prioritize water output or prioritize power output. Though more complex, this design leverages the strengths of both cycles for maximum benefit. Hybrid OTEC is a versatile, integrated solution for communities needing both energy and water. OTEC plants rely on massive pipes to move warm surface water, cold deep water, the lifeblood of the system. The cold water pipe is the most challenging, often over a kilometer long up to 10 meters wide. It must withstand deep-sea pressures and remain flexible. Advanced composites like glass fiber reinforced plastic provide strength, lightness, corrosion resistance. Pipes are built in sections with flexible joints and thick insulation to keep the cold water from warming as it rises. Even slight temperature increases reduce efficiency, so every detail from material to insulation is meticulously engineered. The cold water pipe is a marvel of engineering, bridging the ocean's thermal divide. These pipes are the backbone of OTEC, enabling the entire process. Heat exchangers, usually titanium plate and frame designs, transfer energy between seawater streams with maximum efficiency and minimal resistance. Titanium resists corrosion and biofouling, ensuring long-term performance. Powerful high-efficiency axial flow pumps move huge water volumes, but their energy use, parasitic load, can make or break a plant's net output. Variable frequency drives optimize pump speed, matching flow to real-time needs and saving energy. Every improvement in pump efficiency directly increases usable electricity. Every improvement in heat exchanger efficiency directly increases usable electricity. The battle for OTEC's success is won or lost in these critical components. At the center of the OTEC engine room is the turbine, the device that converts the energy of the expanding working fluid into rotating mechanical power. Visual. The design of this turbine is dictated by the unique physics of the OTEC cycle. Unlike a conventional power plant that uses high-pressure, high-temperature steam, an OTEC turbine operates in a world of low-pressure ratios and modest temperature drops. In a closed-cycle system using ammonia, the vapor is dense and expands with moderate force. In an open-cycle system, the low-pressure steam is diffuse and expands gently. Each system requires a turbine tailored specifically to its conditions, but both demand exceptional efficiency and mechanical precision. OTEC turbines are characterized by their meticulous design to minimize every possible source of energy loss. The blades are sculpted with advanced aerodynamic profiles to ensure the vapor flows smoothly over their surfaces, transferring the maximum amount of momentum. The seals that contain the vapor within the turbine casing must be nearly perfect to prevent leaks, which would represent a direct loss of power. The bearings that support the rapidly spinning shaft must be incredibly low friction, often using magnetic levitation or specialized materials to reduce mechanical drag to an absolute minimum. In the low-margin world of OTEC, these small, incremental gains in efficiency add up to make a significant difference in the plant's overall output. The rotating shaft of the turbine is coupled to a generator, the machine that performs the final conversion of mechanical energy into electricity. For offshore plants, where simplicity and reliability are paramount, direct drive generators are often preferred. These generators are designed to operate at the same speed as the turbine, eliminating the need for a gearbox, which is a common point of mechanical failure and energy loss. Permanent magnet generators are also increasingly common, as their high efficiency and compact size make them well suited for the space-constrained environment of a floating platform. The entire assembly must be robustly protected from the corrosive salt mist atmosphere of the ocean environment. The final step is to ensure this power is usable. The electricity produced by the generator is fed into a suite of power electronics. These solid-state devices condition the raw power, converting it to the precise voltage and frequency required by the electrical grid it will supply. For offshore plants, this conditioned power is then sent through a high-voltage subsea cable to shore. For onshore plants, it is fed directly into the local utility network. The turbine and generator assembly is the beating heart of the plant's power block, a quiet, humming testament to the precision engineering needed to turn a gentle thermal gradient into stable, grid-quality electricity. An OTEC plant needs a physical foundation, a stable base from which to operate. In the dynamic ocean environment, this foundation can take several forms. For locations with steep offshore geography, where deep cold water is found very close to the coast, a land-based plant is often the most practical choice. These plants are built on shore, simplifying construction, maintenance access, and grid connection. Massive intake and discharge pipes are tunneled or laid along the seabed to reach the warm and cold water sources. This offers stability and convenience, but only in a limited number of ideal locations around the world. For most other sites, the plant must be offshore on a floating platform. These platforms are massive engineering structures, like offshore oil and gas rigs, but adapted for OTEC. Ship-shaped vessels, semi-submersible platforms with large stabilizing columns, circular spar buoys. The structure must provide a stable base for heavy machinery, and safely manage the long, heavy cold water pipe hanging below. The platform is moored to the seabed with heavy chains and anchors, designed to withstand severe storms and hurricanes. Materials and maintenance underpin the design. The ocean is unforgiving. Saltwater, constant motion, biological activity. Corrosion is the primary enemy. Materials are chosen with extreme care: titanium for heat exchangers, stainless steel alloys for pumps and valves, advanced composites for pipes and structural components. These are supplemented by active corrosion prevention systems like cathodic protection. Anti-fouling coatings are applied to pipes and intakes to prevent marine growth that could clog the system. Maintenance in this harsh environment must be smart and proactive. Modern OTEC designs incorporate thousands of sensors to create a digital twin of the plant, a virtual model that mirrors real-world operation. This allows operators to monitor the health of every component in real time. AI and machine learning predict when a pump bearing is beginning to wear, or when a heat exchanger needs to be cleaned. Maintenance increasingly uses underwater robotic crawlers and aerial drones. Robots and drones can inspect pipes, hulls, and moorings without risky, costly human intervention, ensuring the plant can continue its quiet, steady work for decades. When you build a facility that moves millions of liters of seawater every minute, you assume a profound responsibility to be a respectful guest in the marine environment, not a disruptive conqueror. The philosophy of modern OTEC design is built around this principle of stewardship. It begins at the very point of contact the water intakes. To protect marine life, the intake screens are designed with very low through-screen velocities, typically slower than 0.15 meters per second. This gentle suction allows fish larvae, other small organisms, to easily swim away, preventing them from being trapped or drawn into the plant's systems. This simple but critical design choice demonstrates a commitment to coexisting with, rather than overwhelming, the local marine ecosystem from the very start. The next critical consideration is how the water is returned to the ocean. The plant discharges two streams: surface water that is now a few degrees cooler, deep water that is now a few degrees warmer. If simply released at the surface, this could create persistent thermal plumes that might alter local habitats. To prevent this, the discharge water is returned to the ocean at carefully selected depths through specially designed diffusers. These diffusers are engineered to mix the discharged water rapidly with the surrounding ocean, ensuring that it quickly reaches a neutral temperature and density. The goal is to return the water to a depth where its new temperature matches the ambient conditions, preserving the ocean's natural thermal stratification and preventing any lasting impact on the water column. Another potential environmental concern is the nutrient content of the deep ocean water. This water is rich in nitrates, phosphates, silicates, essential nutrients that are scarce in the sunlit surface layers. Releasing this nutrient-rich water at the surface could trigger an artificial algal bloom, disrupting the local food web. Therefore, the discharge depth is managed with extreme care. By returning the water to a depth below the photic zone, the sunlit layer where photosynthesis occurs, the nutrients remain locked in the deeper, darker waters, preventing unwanted biological stimulation. This careful management ensures that OTEC's operation does not inadvertently fertilize the surface ocean, maintaining the natural balance of the local marine ecosystem with precision. Finally, the physical presence of the plant itself is designed to be as unobtrusive as possible. The noise from pumps and turbines is a potential disturbance to marine mammals, other acoustically sensitive creatures. Modern OTEC plants address this by mounting machinery on vibration-isolating foundations and enclosing it in sound-dampening housings. The goal is to keep the plant's acoustic footprint to a minimum, ensuring it operates as a quiet neighbor. Continuous environmental monitoring is the final piece of this stewardship puzzle. Sensors constantly track water temperature, salinity, nutrient levels, local plankton populations, providing real-time feedback that allows operators to verify their models and adjust operations if necessary, closing the loop on a truly responsible design. The value of an ocean thermal energy conversion plant extends far beyond the kilowatts it sends to the electrical grid. The very process of generating power creates a cascade of valuable co-products that can fundamentally transform the well-being and resilience of coastal communities. Photorealistic CGI cutaway, the OTEC plant producing power and co-products. The most significant of these is desalinated freshwater, a direct output of open-cycle and hybrid OTEC systems. In many tropical island nations and arid coastal regions where OTEC is most viable, freshwater is an incredibly precious and often scarce resource. By providing a steady, reliable source of pure water, OTEC can reduce dependence on rainfall, reduce dependence on expensive imports, or reduce reliance on energy-intensive reverse osmosis plants, ensuring water security for drinking, sanitation, public health. This newfound water security creates a ripple effect throughout the local economy, most notably in agriculture. The availability of desalinated water can support modern, efficient farming techniques like hydroponics and drip irrigation, allowing communities to grow high-value crops that were previously impossible to cultivate. This can lead to greater food self-sufficiency, reducing the reliance on imported produce and creating a more resilient local food system. Imagine greenhouses filled with fresh vegetables and fruits, irrigated by water that was generated as a byproduct of the island's own clean energy production. This synergy between energy, water, and food creates a powerful foundation for sustainable local development, boosting both nutrition and economic opportunity. The benefits continue with the cold, deep seawater itself. After it has passed through the plant's condenser, this water is still profoundly cold. This creates an opportunity for a highly efficient form of air conditioning known as seawater air conditioning, or SWAC. The cold seawater can be piped to a central heat exchanger on shore, where it chills a closed loop of fresh water. This chilled fresh water is then circulated to nearby buildings such as hotels, hospitals, data centers, and government offices to provide cooling. This process can reduce the electricity needed for air conditioning by up to 90%, a staggering saving that cuts costs, reduces peak demand on the grid, and further lowers the community's carbon footprint. Furthermore, the nutrient-rich deep seawater, if managed responsibly, can become the foundation for a thriving aquaculture industry. Algae, oysters, abalone, salmon, flounder. This creates a new, sustainable industry that can provide skilled jobs and valuable export products, diversifying the local economy away from a narrow reliance on tourism or other single sectors. These co-products are not just side benefits, they are integral to OTEC's value proposition, turning a single power plant into a multifaceted engine for community prosperity and resilience. An OTEC plant is more than just a piece of industrial hardware. It has the potential to become the anchor tenant for a comprehensive blue economy campus. It can serve as the central hub around which a whole ecosystem of industries can develop. The stable, 24/7 power from the OTEC plant provides the reliability needed to attract advanced industries. Constant clean electricity, abundant cold water for cooling makes OTEC-adjacent sites ideal for a data center. This vision extends into science and research. The OTEC plant itself is a unique laboratory, constant access to surface and deep water. Study deep ocean ecosystems. Monitor ocean chemistry and climate impacts. Develop new aquaculture technique. This links industry, research, and education, creating opportunities for local students. Steady baseload power is perfect for green hydrogen. Overnight excess capacity can run electrolyzers. Electrolyzers split desalinated water into hydrogen and oxygen. Store the green hydrogen. Use it to fuel ferries, fuel buses, power port vehicles, or export it as a clean commodity. Ultimately, OTEC's greatest value is integration. Outputs become inputs for other processes. Electricity powers communities and industries. Freshwater supports agriculture and public health. Cold deep water provides efficient cooling and supports aquaculture. Steady power creates green hydrogen. A web of connections builds a resilient, self-sufficient local economy. The OTEC plant becomes a community symbol of an innovative, harmonious relationship with the sea. The concept of harnessing the ocean's thermal gradient is not a futuristic dream. It is an idea with a long and fascinating history, marked by visionary pioneers and steady, incremental progress. The journey from theory to reality began more than a century ago, but it was in the 1930s that the first significant attempt was made. French inventor Georges Claude, a student of Jacques-Arsène d'Arsonval, built an experimental open-cycle plant in Cuba. While the plant ultimately produced very little net power, it was a landmark achievement. Claude demonstrated you could make steam from warm seawater under a vacuum and spin a turbine. His efforts laid essential groundwork for future OTEC development. Decades later, after the 1970s oil crisis, interest surged. The focus shifted to the Pacific, especially Hawaii, with easy access to deep cold water. At Nella, a series of experiments took place. In 1979, Mini OTEC was deployed on a barge off the coast. It was the first closed-cycle OTEC to produce net positive power. That success kicked off research into heat exchanger design, cold water pipe materials, and biofouling prevention. Japan became another key player, launching research programs and pilot projects. Researchers worked on heat exchanger efficiency and cold water pipe tech, often with island partners like Nauru and the Republic of Palau. These small projects taught invaluable lessons about long-term operation. They provided data on material durability maintenance strategies and the complex dynamics of mooring large structures and pipes. Today, that legacy continues. A 100-kilowatt closed-cycle plant at Nella now connects to the U.S. grid. Okinawa hosts a continued demonstration plant in Japan. Projects are being explored in the Caribbean and across the Pacific, often pairing OTEC with desalination and aquaculture. Each project, big or small, builds on past lessons, moving OTEC toward commercial viability. As OTEC technology matures, it naturally invites practical questions about its scale, resilience, efficiency. One of the most common questions is about size. How large is a typical OTEC plant? The demonstration projects built to date have been relatively small, hundreds of kilowatts, a few megawatts. These are crucial for proving the technology and refining designs. But the commercial vision is much larger. Tens of megawatts, floating platforms of 100 megawatts or more. That requires ramping up manufacturing for heat exchangers, specialized composite cold water pipes. Can these plants withstand storms and hurricanes? It's a central offshore design challenge. Modern OTEC platforms use rig-grade engineering redundant seabed moorings designs to survive extreme weather. Platforms can be partially submerged or rotate to face swells. Cold water pipes use flexible joints to absorb motion. Land plants harden intakes and controls and build above projected storm surge lines. What about marine life? Will OTEC harm ecosystems? Thoughtful design is the answer. Intake velocities are kept extremely low so fish and larvae can swim away safely. Discharge is managed with diffusers mixing rapidly at depths, matching new temperature and density. Returning nutrient-rich deep water below the sunlit zone prevents algal blooms. Continuous environmental monitoring creates a feedback loop to keep operations respectful to the marine neighborhood. Finally, efficiency. With a theoretical maximum efficiency of only a few %, is OTEC truly viable? It is crucial to look beyond this single number. Infographic: Carnot efficiency, OTEC versus fossil. Infographic: OTEC capacity factor versus solar, wind intermittency. While the thermodynamic efficiency is low compared to a high-temperature fossil fuel plant, OTEC's great strength is its incredibly high capacity factor. It produces continuous power, 24 hours a day, 7 days a week. For an island nation dependent on expensive diesel fuel shipped across thousands of kilometers, the steady, predictable, and fuel-free power from OTEC can be highly competitive. Add co-products, freshwater district cooling, aquaculture, and the overall economic and social efficiency becomes a very compelling proposition. To truly understand OTEC, let us imagine a day in the life of a modern operational plant. A 10-megawatt facility floating peacefully in the tropical sea. The day begins before dawn, as a continuation of the night's steady hum. In the digital control room on the platform, the automated control system performs its morning checks. In the digital control room remotely on shore, the automated control system performs its morning checks. It analyzes data from thousands of sensors, noting a microscopic increase in biofilm on the evaporator plates overnight. The system makes a tiny adjustment, nudging up the warm water pump speed by 1% to maintain the target heat transfer rate, ensuring the net power output remains perfectly stable as the island's morning demand begins to rise. As the sun climbs higher, the surface water of the ocean warms by a fraction of a degree. The control system detects this subtle shift immediately. The ammonia working fluid begins to vaporize slightly more vigorously in the evaporator. To maintain optimal efficiency, the system responds by slightly trimming the flow of cold, deep seawater to the condenser. On shore, the community is waking up. The local hospital's air conditioning system is already running at peak efficiency. Its chillers cooled not by power-hungry cooling towers, but by a steady stream of cold water diverted from the OTEC plant's massive deep-sea pipe. By midday, the plant is operating at its full, steady capacity, a reliable anchor for the island's power grid. Split screen, floating OTEC at midday, bustling hydroponic greenhouse caption, power and water for a sustainable community. In a nearby greenhouse, misters spray rows of lettuce with pure, desalinated water produced by the plant's open-cycle component. In the same greenhouse, misters spray rows of tomatoes with that same pure water. Out at sea, a small fishing boat passes the platform. The structure has become a familiar landmark. Its gentle eddies are known to attract schools of mahi-mahi and schools of tuna. In the afternoon, a sudden squall kicks up choppy waves. The platform, designed for this, gently pitches and heaves, its massive mooring lines holding it securely in place. The flexible joints in the kilometer-long cold water pipe absorb the motion gracefully, and the power output to the grid barely flickers. As evening falls and electricity demand on the island begins to decrease, the plant's role shifts. The control system diverts a fraction of the electricity, perhaps 2 megawatts, to a bank of electrolyzers located at the port. These machines quietly begin splitting the plant's freshwater output into hydrogen and oxygen. The green hydrogen is compressed and stored in tanks on the pier, ready to refuel the island's public buses the next morning, and ferries. Through the night, the OTEC plant continues its silent, steady work, a tireless engine powered by the ocean's enduring thermal rhythm, providing not just power, providing water, providing cooling, providing clean fuel for the community it serves. The ocean's enduring rhythm keeps it all running. The vision for OTEC's future is clear and compelling, but transforming it from successful demonstrations into a widespread global energy source requires a strategic roadmap. The first and most critical step is achieving scale. Mass production is the key to driving down costs. The OTEC industry must move towards standardized modular designs. Factories producing interchangeable heat exchanger cassettes, pre-packaged turbine generator units, standardized sections of composite cold water pipe, from bespoke projects to streamlined manufacturing and assembly. The second pathway on the roadmap is deeper integration. OTEC can be more than just a power plant. Co-locate with floating solar farms, co-locate with offshore wind turbines, share mooring systems, share transmission cables, share maintenance crews, hardwire OTEC into urban planning district cooling networks for coastal developments, freshwater for municipal systems, cold, nutrient-rich water to aquaculture parks, cold, nutrient-rich water to marine research centers. This integrated approach maximizes the value of every drop pumped. Smart policy and innovative finance are essential. Governments in island nations and coastal states can create the stable regulatory environment needed to attract investment. Long-term power purchase agreements that value OTEC's round-the-clock reliability can provide revenue certainty. International development banks and climate funds can play a crucial role in de-risking the first wave of ATE. Commercial-scale projects, loan guarantees blended. Financing market mechanisms to reward OTEC co-products, carbon credits for displacing diesel, water credits for desalination. Finally, the roadmap must be centered on people. Training programs at local universities, training programs at technical colleges, partnerships with local businesses to build the supply chain, community ownership models, revenue-sharing agreements. When communities see OTEC as their source of power, water, and opportunity, the blue future has arrived. We began this journey by listening for a sound we could not hear, the silent, steady heartbeat of the ocean. It is a rhythm born not of muscle and blood, but of thermal energy, a constant and profound difference between the sun-warmed surface and the frigid, dark abyss. This gentle temperature gradient, a mere 20 degrees Celsius, represents one of the planet's largest and most reliable energy reservoirs. Ocean thermal energy conversion is the remarkable key that unlocks this reservoir, transforming a subtle, ever-present difference into a powerful and continuous stream of clean electricity. It is a technology that does not chase the unpredictable gusts of the wind or wait for the sun to rise from behind the clouds. Instead, it leans into the ocean's fundamental daily rhythm, a rhythm that has persisted for millennia and will persist for millennia to come. Throughout this exploration, we have journeyed from the core principles of thermodynamics to the intricate engineering of its hardware. We have seen how OTEC works with nature on its own terms, using low pressures to make water boil at room temperature and harnessing the resulting vapor with turbines of immense precision. We have followed the path of the working fluid in a closed cycle, and the seawater itself in an open cycle, each pathway offering a unique blend of power and co-products. This is not a technology of brute force, but of immense finesse. It is a system where every degree of temperature is precious, every component is optimized for minimal loss, and every joule of energy is treated with respect. The result is a power source of unparalleled stability, a quiet workhorse for a world in need of reliable, clean energy. The story of OTEC is more than a tale of ingenious engineering. It is a narrative of environmental stewardship. It demonstrates how we can design large-scale energy infrastructure to be a guest in the ocean, not an intruder. By using slow intake velocities, carefully managed discharge diffusers, and sound-dampening technology, an OTEC plant can integrate into the marine ecosystem with a minimal footprint. It is a testament to a new way of thinking, where our energy systems are designed in harmony with the natural world, drawing power from its fundamental processes without disrupting them. This careful, respectful design philosophy is what elevates OTEC from just another renewable energy source to a potential model for sustainable development in the 21st century. As we conclude, we are left with the profound simplicity of the core idea. The ocean holds a vast, stored energy in its thermal layers. OTEC provides the means to tap into it. By exchanging heat with care, spinning a turbine with efficiency, and returning the water gently to the sea, we can power coastal communities around the clock. This is not science fiction. The principles are proven, the hardware has been tested, and the potential is immense. The quiet heartbeat of the ocean is waiting. It offers a steady, clean, and enduring source of power, a rhythm that can help us build a more sustainable and resilient future for generations to come. The true promise of ocean thermal energy conversion lies in its power to transform potential into prosperity. For the island nations' tropical coastal regions, OTEC is not just an alternative to expensive, imported fossil fuels. It is a catalyst for comprehensive economic and social development. The electricity it produces is the foundation: clean, stable, locally sourced. This energy independence frees economies from volatile oil price swings and provides reliable power for modern infrastructure, education, healthcare. But the story does not end with the electron. The true magic of OTEC is in the cascading benefits anchoring a vibrant blue economy. The co-products of OTEC turn a power plant into a community life support system. Water scarcity is a growing crisis. Open ice cycle systems, hybrid systems, can produce vast quantities of desalinated freshwater. This water can green deserts, support local agriculture, and give every citizen clean drinking water. Cold, nutrient-rich deep seawater used for condensation becomes cooling for buildings and a medium for high one-value aquaculture. This synergy, energy plus water, food, cooling, creates self-sufficiency and resilience. A diverse ecosystem of new industries and skilled jobs emerges. Opportunities arise for marine engineers, aquaculture technicians, data center operators, hydrogen fuel specialists. It builds a knowledge economy around a sustainable hub, offering young people a future at home. An OTEC plant can anchor a research campus, a data hub, a food production center, a clean transport network. It embodies a circular economy. Outputs become inputs, minimizing waste. Not a standalone machine on the horizon, but the beating heart of a thriving coastal society, empowering communities to leverage the tropical ocean to build a cleaner, more prosperous, equitable, resilient future. The path to decarbonization needn't be sacrifice, it can be innovation and opportunity, powered by the gentle energy offshore. OTEC offers a tangible pathway from resource potential to shared community prosperity. We stand at a critical juncture in human history, facing the dual challenges of a changing climate and the growing energy demands of a developing world. The solutions we choose in the coming decades will define the planet our children and grandchildren inherit. While solar power, wind power, their intermittent nature leaves a critical gap, ocean thermal energy conversion is uniquely positioned to fill that role, providing the steady, 24/7 baseload power. It can stabilize grids, support heavy industry, and complement other renewables. The path forward is implementation and scale. The scientific principles are understood, the engineering challenges identified, and the pilot projects have proven the concept. The roadmap is clear. Standardized designs, build dedicated manufacturing supply chains, deploy commercial-scale plants. This requires smart policies that recognize the full value of OTEC's reliability and its co-products and innovative financing to de-risk these pioneering projects. The journey will require investment, persistence, and political will, but the destination is worth the effort. Imagine a future, perhaps in 2040 or 2050, where a ring of OTEC platforms encircles the globe's tropical belt. These silent, steady sentinels are the anchors of energy security for hundreds of millions of people in coastal communities from the Caribbean, Pacific Islands, Southeast Asia. They provide not just power, the fresh water that sustains cities, the cooling that runs digital infrastructure, and the green hydrogen that fuels clean shipping. In this future, the ocean is no longer just a space to be crossed or a resource to be extracted, but a collaborative partner in a sustainable global civilization. This is the potential that lies before us. The time for hesitation is over. The ocean's quiet power offers us a profound opportunity. It is a chance to build a more resilient and equitable world, powered by an energy source as constant and enduring as the ocean itself. We have explored the science, we have examined the engineering, and we have seen the vision of what is possible. What remains is for us to act, to invest in the technology, to build the partnerships, and to have the courage to scale a solution that works in harmony with our planet. The dawn of a blue century is upon us, and its power source is the gentle, hidden, and unwavering heartbeat of the sea.